Let's start off with this integral by rearranging it, right? We are going to have I to be equal to the integral from 0 to infinity of the tan inverse, right, of x squared. 5 can be written as 1 plus 4, right? And then I'm going to bring the 2x here, dx. This one is divided by x squared plus 1, all this one squared. All right, so now let's do our first substitution. All right, so I am going to let let's say u to be equal to x squared plus 1. When I do this, du is going to be equal to 2x dx. All right, so now the change in limit. When x is equal to 0, which is the lower limit, u is going to be 1. That is 0 squared plus 1. And when x is equal to infinity, we have u to be equal to infinity as well. So the integral in the u world is now looking like this. I is going to be the integral from 1 to infinity now. So the integral from 1 to infinity of the tan inverse of x squared plus 1 is u, that is this one, that is u plus 4. And this one is divided by u squared. And 2x dx is the same as du. That is what we have here. And now we can do another substitution. Why not? So our second substitution, we are going to let's go back to x. We are going to let x to be equal to u plus 4. Right. When we do this, that means u is going to be equal to x minus 4, and then du is going to be equal to dx. And now the change in limits. When u is equal to 1, that is the lower limit, x is going to be equal to 1 plus 4, which is 5. When u is equal to infinity, x is going to be equal to infinity as well. Okay, so now the integral in the x world, we are back to x for the sake of convenience. So this is now the integral from 5 to infinity of the tan inverse of u plus 4. U plus 4 is the same as x. This is divided by u squared. U is x minus 4. So that is x minus 4. This is squared, and then du is the same as dx. That is what we have. All right, so now after here, I'm going to do integration by parts. So di, so the di method. So d for differentiation, I for integration. I am going to differentiate the tan inverse of x. Why not? This is plus, next one is minus. Differentiating tan inverse of x is 1 all over 1 plus x squared. Cool. And now I'm going to integrate the rest, which is 1 over x minus 4 all squared. And what about integrating this? This is negative 1 all over x minus 4, right? That is the integral of this guy. So we can use a u-sub. So that means, I'm just going to do it here real quick. We have the integral of dx all over x minus 4 all squared, right? So we can do a u-sub. We can let u to be equal to x minus 4. And when we do this, that means du is going to be equal to dx. So that means there is going to be the integral of du all over u squared. And integrating 1 over u squared is negative 1 over u. And replacing back, that is going to be negative 1 all over u is x minus 4. So that's what we have. Alright, so now we're now going to apply integration by parts. Multiplying diagonal terms, we are done with the integration. But when we multiply terms horizontally, we have to take the integral. So we have I to be equal to negative tan inverse, right, of x. This is divided by x minus 4. We are done with the integration. Take the limits of integration from 5 to infinity. And now negative, that's positive. That's going to be plus the integral from 5 to infinity of multiplying terms horizontally. That is going to be 1 all over x minus 4, which is multiplied by 1 plus x squared. All this 1 dx. All right, so now let's plug in the limits. So you have negative out. Now let's take the limit as x approaches infinity of the tan inverse of x. This is divided by x minus 4, right? And then minus the lower limit, we are going to have the tan inverse of 5. So tan inverse of 5 divided by 5 minus 4, like this. These are the limits, and now you add the integral from 5 to infinity of 1 all over x minus 4, and this is multiplied by 1 plus x squared dx. Alright, so this is what we have. Now the limits, what does it simplify to? So as x is approaching infinity, tan inverse of x is going to be approaching pi over 2. And x minus 4 is going to be approaching infinity. So pi over 2 over infinity is going to be 0. So this one is going to be approaching 0 as x approaches infinity, minus tan inverse of 5, because this is 1. This is what we have, and then plus the integral from 5 to infinity of 1 all over x minus 4, and this is multiplied by 1 plus x squared dx. So far so good. So I is going to be equal to, this is now the tan inverse of 5, negative, negative, right? And then plus the integral from 5 to infinity of 1 all over x minus 4, and then multiplied by 1 plus x squared dx. This is partial fractions, right? So let me call that one integral I1. Why not? Now let's switch colors and solve that. So we have I1 to be equal to, so first of all, I'm going to simplify the integrand using partial fractions, and then I'll come back later on for the integral. Multiplied by this, and now using partial fraction, that's going to be a over the first one, x minus 4, and then bx plus c. This is divided by 1 plus x squared, the quadratic term. So 1 all over x minus 4 multiplied by 1 plus x squared. This is the same as cross multiplication, a times 1 plus x squared plus bx plus c. And this is multiplied by x minus 4. All this one divided by the LCM, x minus 4, and then 1 plus x squared. Cool. Now the denominators are the same, so we just have to focus on the numerators. So this is a plus ax squared. I'm just expanding here, right? And then plus foiling that, that is going to be bx squared minus 4bx plus cx minus 4c. Now let's gather like terms. That is going to be a plus b, right? A plus b is the coefficient of x squared. What about the coefficient of x? That is going to be c minus 4b. Right, this is the coefficient of x, and the constant term is a minus 4c. Now we can compare both sides. That is going to be, so the coefficient of x squared, a plus b on the right hand side, is equals to 0. This is equation 1. There is no x squared term on the left hand side. C minus 4b, the coefficient of x on the left hand side, is 0 as well. The coefficient of x on the left hand side is 0, and the constant term a minus 4c on the right hand side is equals to 1, the constant term on the left. And now solving these three equations simultaneously, the value of a, b, and c that will satisfy them will be: a is 1 over 17, b is negative 1 over 17, and c is going to be equal to negative 4 over 17. You can verify that these values are true. That is by putting them in here. You satisfy all the three equations. Alright, now that we have this, let's go back to our partial fractions and see what the equation will be. So we have 1 all over x minus 4. This is multiplied by 1 plus x squared. And this is the same as a over x minus 4. And a is 1 over 17. So 1 over 17, this is divided by x minus 4. Right, and the next one is bx plus c divided by 1 plus x squared. Bx plus c, so that is negative 1 over 17x plus c, and that is minus 4 over 17 divided by 1 plus x squared. This is our partial fraction decomposition. So we have 1 all over x minus 4 multiplied by 1 plus x squared. This is 1 over 17 times 1 over x minus 4 minus 1 over 17 times x over 1 plus x squared, and then minus 4 over 17 multiplied by 1 over 1 plus x squared. This is how you can write our integrand. And now let's switch back and now solve the integral. So we're coming back here. So that is I. This is equal to the tan inverse of 5, right? And now plus the integral, plus the integral from 5 to infinity, plus the integral from 5 to infinity of this, which is the same as that. So that is going to be 1 over 17 times 1 over x minus 4 minus 1 over 17 times x over 1 plus x squared minus 4 over 17 times 1 over 1 plus x squared, all this one dx. Cool. All right, so I is going to be equal to, this one is a constant, we just write it along. So the arctan of 5. Now let me split this one into 3 different integrals. You have 1 over 17. It's a constant, the integral from 5 to infinity of 1 over x minus 4 dx. Next one is going to be negative 1 over 17, but permit me to multiply this integral by 1/2, and then I'm going to nullify the effect by multiplying the numerator by 2. That is going to be divided by 1 plus x squared and then dx. These 2 and these 2 cancel, so that preserves the integral. This is from 5 to infinity. And then the last one is going to be minus 4 over 17, the integral from 5 to infinity of 1 over 1 plus x squared and then dx. These are the 3 different integrals. I is going to be equal to the tan inverse of 5. And now plus, this is 1 over 17. So the derivative of this is the numerator, so this is the ln of x minus 4. Minus 1 over 34, that is 17 times 2. And now this is the ln of 1 plus x squared. That is the derivative of this is the numerator, minus 4 over 17. And then this is the arctan of x. You are done, you can put the limits of integration from 5 to infinity. I is going to be equal to the tan inverse of 5. Correct. And now here, this 1 over 17, I'm going to multiply the numerator by 2 and then multiply the denominator by 2. So 1 over 17 is the same as 2 over 34 minus 1 over 34 here. The ln of x squared plus 1, can write it that way, minus 4 over 17. And then I'm going to have the tan inverse of x, the limits of integration from 5 to infinity. I is going to be equal to the tan inverse of 5. Alright, so here using the laws of logarithm, that is going to be, this 2 is going to become a power here, right? Using the power rule of logarithm. So that is going to be left with 1 over 34 in front here. And now we have the ln of x minus 4 squared. Right, but x minus 4 squared, if you FOIL that, that is going to be x squared minus 8x plus 16 minus 1 over 34, the ln of x squared plus 1 minus 4 over 17, and then the arctan of x, the limits of integration from 5 to infinity. Now let's do some factorization and apply the laws of logarithm. So 1 over 34 is common between these two terms. So I'm going to factorize 1 over 34 out. So 1 over 34, then I'm going to use the laws of logarithm. That is going to be the ln of x squared minus 8x plus 16. This is divided by x squared plus 1. Right, minus 4 over 17. This is multiplied by the arctan of x, the limits of integration from 5 to infinity. We are now going to plug in the limits of integration. So the first one is a constant, it doesn't matter. So the tan inverse of 5. And now we are going to take the limit. So we are going to have plus 1 over 34. Why not? And now we are going to have this, the limit as x approaches infinity of the ln. Because we are taking limit as x approaches infinity, I'm going to divide the numerator and denominator by x squared. Minus 8x plus 16 divided by x squared, and I'm going to do the same thing to the denominator, divided by x squared, to maintain equality, right? And then minus, that is the upper limit, minus the lower limit, right? The lower limit, when you plug in 5, that is going to be the ln of 5 squared minus 8 times 5 plus 16. This is divided by 5 squared plus 1. This is what we have for the lower limit. All this is multiplied by 1 over 34 in front. Alright, minus 4 over 17. Right, I'm running out of room here, so what I'm going to do is I'm going to take the limit as x approaches infinity of the tan inverse of x. Right, so this is the upper limit minus the lower limit. You plug in infinity 5, that is going to be the tan inverse of 5. I'm running out of room, please forgive me for this. Alright, so I is going to be equal to the tan inverse of 5. plus 1 over 34, right? And now this is going to be the ln of the limit, because the ln, natural logarithm, is a continuous function. I can bring in the limit as x approaches infinity of, now dividing this is going to be 1 minus 8 over x plus 16 over x squared, and the denominator is going to be 1 plus 1 over x squared, like this, right? Minus ln of what? 5 squared minus 8 times 5 plus 16, that is 41 minus 40, which is 1 over 25 plus 1 is 26, like this. This is multiplied by this, and then half minus 4 over 17, right? And what do I have here? As x is approaching infinity, tan inverse of x is going to be approaching pi over 2 minus tan inverse of 5. Okay, cool. I is going to be equal to the tan inverse of 5 plus 1 over 34, right? So as x is approaching infinity, this is 0, this is 0, right? And this is 0. So what is left is just 1 over 1, and 1 over 1 is 1, and now you are going to have the ln of 1. Ln of 1 is 0, so this one is just 0. So this is 0 minus the ln of 1 over 26, and ln of 1 over 26 can be written as this, negative ln of 26, like that. And now minus 4 over 17, and this is multiplied by pi over 2 minus the tan inverse of 5, like this. Cool. I is going to be equal to the tan inverse of 5, and now this negative, that's positive, right? So that is going to be plus 1 over 34 times the ln of 26, and now minus 4 over 17. This one, let's use this property, right? If you are having this, the tan pi over 2 minus the tan inverse, right, of a over b, this is the same as the tan inverse of b over a, right? So pi over 2 minus the tan inverse of a over b is the same as the tan inverse of b over a. So this one is pi over 2 minus the tan inverse of 5 is the same as the tan inverse. This is the same as the tan inverse of 1 over 5, because this one is like 5 over 1, right? All right, so I is going to be equal to the tan inverse of 5 plus 1 over 34, the ln of 26, minus 4 over 17, right? Tan inverse of 1 over 5 is the same as cotangent inverse of 5, right? We have to also use this property, right? So if we have the tan inverse of a over b, right, this is the same as the cotangent inverse of b over a. We are going to use this one to simplify this one. So the tan inverse of 1 over 5 is the same as the cotangent inverse of 5, like this. So now to make everything have the same coefficient, so I'm going to multiply this one by 34 and divide by 34, and that is going to be multiplied by the tan inverse of 5, and then plus 1 over 34 here, that is going to be the ln of 26, minus, this is 8 over 34, right? And then the cotangent inverse of 5. Okay, all right, so we have I to be equal to, now see that 1 over 34 is common. I'm going to factorize 1 over 34 out, and what is left here is the ln of 26 plus 34 times the tan inverse of 5 minus 8 times the cotangent inverse of 5, and this is consistent with the answer that Wolfram alpha is given. Yeah, so that is the answer to this beautiful integral. 1 over 34 times the ln of 26 plus 34 times the tan inverse of 5 minus 8 times the cotangent inverse of 5. And that is how I solved this beautiful integral. If you have an easier way to solving this, please put your comment in the comment section and let me know what you think. And if you really enjoyed this video, if you learned something new, please give me a thumbs up and consider subscribing to Calculus Diaries for more engaging content on calculus. I thank you so much for watching this video, and I will catch you up in the next one. Bye bye.